Alright, today we have gas laws. Now, with gas laws, those are the things that have been around for 300 years. You know, back when the early chemistry days, after they got done with alchemy and the false chemistry, they got into gas laws. I thought that was kind of cool. They tried to impress their friends, impress their wives, that sort of fun stuff. So, with gas laws, we learned a lot about chemistry. When we talk about gas, we deal a lot with kinetic theory and motion. We have particles that are moving around. So we can think about when we add heat, how do particles react? When we increase the size of a container, how are the particles inside going to react? If we add more, those are all things that we're going to deal with today in gas laws. Okay, we have the combined gas law up here. Now the combined gas law is P sub 1 V sub 1 over T sub 1 equals P sub 2 V sub 2 over T sub 2, which sounds like a complete mess when you say it like that. So we just go PV over T equals PV over T. All we have is conditions that change, resulting in either a pressure change, a volume change, or a temperature change. Now, I guess I just said what the variables are. P is for pressure. That could be any pressure unit, kilopascal, atmospheres, torr, millimeters of mercury. Doesn't matter as long as we're consistent across the board. Okay, volume. Volume can be centimeters cubed. It could be milliliters. It could be liters. Several different things we can use for volume. Again, as long as we're consistent. Now, the one that does matter, though, is whenever we have temperature. Temperature has to be in Kelvin. Okay, and the reason it has to be in Kelvin is because Kelvin is our absolute scale. Okay, so if I show you an example really quick, if I do a ratio and I try to say, well, I have temperature at 1 degree Celsius on this side and 2 degrees Celsius on this side. If I look at that, my temperature has doubled. Okay, so that's what our mindset is there. But in the absolute, it hasn't. 1 degree Celsius is 274 degrees. That's not a degree. 247, or 274, I've gone dyslexic for a moment. 274 K. Okay, 274 Kelvin. 2 degrees would be 275 K. So the ratio doesn't fit as being twice as big. Okay, so our temperature, or our energy, per se, doesn't change there. So we have to make sure that our energy, or our temperatures, are in K. That's going to help us out quite a bit. Okay, we're going to stick with this equation. This equation is going to help us out a lot. If there is any equation you just flat out have to know, it's this one. Okay, so combined gas law. Now, from the combined gas law, I'm going to start dumping out some things. We're going to have constants. If I keep one side constant, if I say that I keep my temperature constant. If I have a temperature on this side is the same on this side, I don't need to do it mathematically, so I might as well just get rid of it. So the first one we're going to talk about is what happens if we keep our temperature constant. And that is where we get Boyle's law. Okay, Boyle's law, we keep temperature constants. So it's going to look just like this. PV equals PV. Okay, it's pretty easy. The reason we're going to remember Boyle's law, if you're thinking about something boiling, what are you thinking about? You're thinking about how hot it is. How hot it is going to tell us the temperature. So Boyle's law, temperature constant. Okay, we'll actually see some things with Boyle's law when you're working on your labs. Okay, I don't want to go too in depth on these because I want you to have some self-discovery when you're actually working these things out. Okay, the next equation, the next thing we're going to keep constant is going to be pressure. Okay, so if I keep pressure constant, our equation is going to look like this. I'm going to try not to cover it up too much. The pressure constant is going to give us V over T equals V over T. That is by Charles. I think it's actually 2 S's like that. Charles's law. Okay, I know it's lame, I know it's terrible. Zach is back there filming thinking, oh God, don't go through this speech. Here's what it is. In the 1980s, Scott Baio sings Scott Baio from Happy Days. Some of you may know Happy Days. It's a long time ago. He was in a show called Charles in Charge. It was a terrible show. Don't watch it on Netflix or anywhere. But Charles was a babysitter. And I will tell you, it is a very important job to be a babysitter. And when you are a babysitter, you are under immense pressure. Charles' law, pressure is constant. Okay, last one. We have one more variable, and that is going to be volume. So if I take volume out, same thing as before, we get the same type of thing. Volume is out. I'm going to go this side now. Volume is out, so we have P over T equals P over T. And that law is Gay-Lussac. It's an L, not a C. I know what you guys are thinking at home. Okay, so Gay-Lussac law. That is the final of our combined gas laws put together. Okay, what we have up here is our ideal gas law. And what we mean by ideal gas is we hope that gases behave ideally. And by that we mean that they move around, they're elastic, 100% elastic. So if they hit an object, they don't just hit the object and start to lose energy. They maintain all that energy, which is very important in some of our theories here. So this equation, ideal gas law, PV equals nRT is what we're going to really call it. So if you hear me say you need to use PV equals nRT or PevNert, whatever it does to help you kind of remember this, use a couple different ideas. Okay, so P, this is going to be pressure. Now pressure in this case, since it's not a ratio, since it's got a constant in it, we'll talk about that constant here in a second, has to be in kPa. Has to. So make sure that your pressure is in kPa. Okay, your volume needs to be in milliliters.
Liters, not milliliters.
Okay. So
Bad
make
info.
sure that your volume is in milliliters.
Volume needs to be in liters once
You're
again.
in. I know we've gone about 1,000 different ways that we can abbreviate the word mole, M-O-L-E, M-O-L, and now we have another one. Here's the symbol for mole in gas loss is in. So this is moles. So however many moles we have, we're going to put that for in. R is our gas constant. I'll get back to that in a second. And then T is going to be our temperature. We need to put that in Kelvin. Okay, so back to our constants. Remember, constants are just used in mathematical equations to make the numbers fit, to make them all come together so we have some meaning, so we can see a trend. The constant here is going to be 8.31. Now, same thing as what we did before. What are the units for it? Okay, so if I want to figure out what the units are, okay, rearrange the equation. I've got N equals PV over RT. What am I doing there? I don't want to solve for moles. I want to solve for gas constant. R equals PV over NT. Okay, pressure is going to be kPa. Volume is milliliters.
Liter, not milliliter.
Moles. K. Okay, so if I want to come up with my units, that's how I do it. Remember, always take what you do know to solve for these more complex, what the heck kind of unit is this? Okay, that gets us through our beginning parts. We still have a couple more gas laws we need to talk about. We need to talk about Dalton's law. It's really easy. We need to talk about Graham's law of diffusion. It's a little bit more difficult. So, we'll get back to that after we're done with our labs this week. Have a great week. Make sure you're